Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the pre-dawn hours of February 4th, 2023, a 7.8 magnitude earthquake struck southern Turkey and northern Syria. Within minutes, thousands of buildings collapsed. Within hours, the death toll reached the hundreds. Within days, over 50,000 lives were lost. The question that haunted seismologists worldwide was both simple and devastating. Could this tragedy have been prevented if we had known it was coming? Earthquake prediction remains one of the most elusive goals in geoscience, a field where success could save countless lives, yet failure could trigger mass panic or dangerous complacency. Unlike hurricanes or floods, earthquakes give few reliable warning signs, often striking without apparent precursors. But what if we could change that? What if we could provide communities with days, weeks, or even months of advanced warning? The science of seismic forecasting stands at a critical juncture, where technological innovation meets ethical complexity. Today's cutting-edge prediction methods combine traditional seismology with artificial intelligence, satellite monitoring, and even animal behavior studies. These approaches offer tantalizing glimpses of a future where earthquakes might no longer ambush vulnerable populations, but they also raise profound questions about responsibility, communication, and the consequences of both action and inaction. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. Throughout human history, earthquakes have been among our most feared natural disasters. Ancient civilizations attributed them to angry gods or mythical creatures. The Japanese believed they were caused by a giant catfish named Namazu thrashing beneath the islands, while Greek mythology blamed Poseidon's trident striking the ocean floor. These supernatural explanations reflected humanity's desperate need to make sense of seemingly random devastation. The modern era of seismic study began in 1889, when the first seismograph capable of remote detection was invented. Since then, our understanding has evolved dramatically through the plate tectonic revolution of the 1960s and today's network of thousands of monitoring stations. We now know that earthquakes occur when stress builds along fault lines until the rock suddenly slips, releasing enormous energy. Yet translating this understanding into reliable predictions has proven exceptionally difficult. The dream of earthquake. Prediction isn't merely academic. When the 7.9 magnitude Great Hanshin earthquake struck Kobe, Japan in 1995, it caused over 6,000 deaths and $100 billion in damage in just 20 seconds. The 2008 Sichuan earthquake in China killed nearly 90,000 people. The Haiti earthquake of 2010 resulted in over 200,000 deaths. In each case, a warning of even hours might have saved thousands of lives. Today, scientists can identify regions at high seismic risk and calculate statistical probabilities over decades or centuries with reasonable accuracy. But specific short-term predictions, identifying where and when a major earthquake will strike within days, remain largely beyond our grasp. This limitation creates the central tension in earthquake science, the gap between what affected communities desperately need and what scientists can responsibly provide. As we explore the frontier of earthquake prediction, we must confront not only scientific challenges but ethical dilemmas. False alarms could cause economic damage and erode public trust. Missed predictions could leave scientists blamed for preventable casualties. The question becomes not just, can we predict earthquakes, but should we try? And if so, how do we handle the awesome responsibility that comes with forecasting disaster? The hunt for earthquake prediction methods spans disciplines and approaches, from underground sensors to space-based technologies. To understand the current state of the science, we must first grasp what happens during an earthquake. Deep beneath our feet, tectonic plates, enormous segments of Earth's lithosphere, are in constant motion driven by convection currents in the semi-fluid asthenosphere below. Where these plates meet, they create fault lines, boundaries where stress accumulates until it exceeds the friction holding the rocks together. The moment of failure, when rock formations suddenly slip past each other, releases kinetic energy in the form of seismic waves that propagate through Earth's crust. Primary or P waves are compressional waves that move fastest. Secondary or S waves travel more slowly but often cause more damage. And surface waves, which travel along Earth's surface, typically create the most destruction. Modern seismometers detect and measure these distinct wave patterns, allowing scientists to locate an earthquake's epicenter and determine its magnitude with remarkable precision, but only after it has already begun. True prediction requires identifying reliable precursors, measurable changes that consistently occur before an earthquake strikes. Numerous candidates have been studied, including groundwater level fluctuations, radon gas emissions, electromagnetic field changes, ionospheric disturbances, and even unusual animal behavior. While some show promise, none has demonstrated the consistency needed for dependable forecasting. In Haicheng, China, in 1975, authorities evacuated the city hours before a 7.3 magnitude earthquake, potentially saving thousands of lives. This success, often cited as evidence that prediction is possible, came after observations of strange animal behavior, foreshocks, and groundwater changes. However, attempts to replicate this success have yielded disappointing results. Just 1 year later, no warning preceded the devastating Tangshan earthquake that killed at least 240,000 people just 400 kilometers away. More recent approaches leverage big data and machine learning. By analyzing patterns in the vast data sets from global seismic monitoring networks, algorithms seek to identify subtle signals that human analysts might miss. One promising avenue involves studying slow slip events, gradual movements along fault lines that sometimes precede major earthquakes. Another focuses on seismic clustering patterns, as large earthquakes are often preceded by distinctive sequences of smaller tremors. Satellite technology has also transformed the field. Interferometric synthetic aperture radar, INSAR, can detect ground deformation of just a few millimeters from space, potentially revealing strain accumulation along fault lines. The Global Positioning System, GPS networks, provide similar insights through ground-based measurements, tracking the infinitesimal movements of Earth's crust over time. Despite these technological advances, the fundamental challenge remains. Earthquakes result from complex, chaotic systems with numerous variables. The stress patterns within fault zones are heterogeneous and largely hidden from direct observation. Predicting exactly when a fault will fail remains comparable to predicting exactly when an overstretched rubber band will snap. We understand the physics, but precise timing eludes us. This hasn't stopped researchers from developing probabilistic forecasting models. These don't predict specific earthquakes, but instead calculate the likelihood of seismic events within geographic regions over various time frames. The United States Geological Survey, USGS, publishes such forecasts, estimating the probability of significant earthquakes in different regions over the next 30 to 100 years. While valuable for building codes and infrastructure planning, these long-term probabilities offer little help during immediate emergency response. Short-term forecasting shows more promise. Early warning systems, now operational in Japan, Mexico, and parts of the United States, detect the first seismic waves from an earthquake and transmit warnings to areas that haven't yet experienced shaking. These systems provide seconds to minutes of warning, not enough for evacuation, but sufficient to stop trains, shut down gas lines, or take shelter under sturdy furniture. They represent not prediction, but rapid detection and communication. Perhaps no earthquake prediction controversy has generated more heated debate than the L'Aquila case in Italy. In the early months of 2009, the historic town of L'Aquila experienced a swarm of small tremors. Local technician Giampaolo Giuliani, using controversial radon measurement techniques, claimed a major earthquake was imminent and began warning residents. His predictions, viewed as alarmist by many seismologists, prompted local authorities to request an assessment from Italy's Major Risks Committee. On March 31st, 6 days before disaster struck, The committee held a meeting now infamous in seismic history. Their conclusion, as communicated to the public, was reassuring. The ongoing tremors were actually releasing energy and reducing the likelihood of a major event. On April 6th, a 6.3 magnitude earthquake devastated L'Aquila, killing 309 people and leaving thousands homeless. The aftermath was unprecedented. 7 members of the Major Risks Committee were put on trial for manslaughter. Prosecutors argued they had provided inexact, incomplete, and contradictory information that led residents to remain in unsafe buildings. In 2012, all 7 were convicted and sentenced to 6 years in prison, though the verdicts against 6 of them were later overturned on appeal. The case sent shockwaves through the scientific community, raising alarming questions about the legal liability of scientists who communicate risk to the public. In stark contrast stands Japan's earthquake early warning system, perhaps the world's most advanced. When the 9.1 magnitude Tohoku earthquake struck off Japan's eastern coast on March 11, 2011, the Japan Meteorological Agency's system detected the initial P waves and issued alerts through multiple channels: television, broadcasts, cell phones, and public address systems. While the warning came just seconds before the strongest shaking began, it allowed many people to take protective action. The earthquake and resulting tsunami still caused nearly 20,000 deaths, but the early warning system is credited with reducing casualties. Japan's approach reflects decades of investment in both technology and public education. Japanese citizens regularly participate in earthquake drills and understand both the capabilities and limitations of the warning system. This cultural context creates an environment where even brief warnings can save lives without causing panic, a delicate balance that has proven difficult to achieve elsewhere. China presents yet another approach to seismic forecasting. Following the successful Haicheng prediction, China established an extensive earthquake monitoring network, combining professional and amateur observers. This system includes not only scientific instruments, but also reports of unusual phenomena like water, level changes in wells, or unusual animal behavior. While Western scientists often dismiss such observations as anecdotal, the Chinese approach integrates multiple data sources in recognition that earthquake precursors might manifest in ways modern instruments cannot yet detect. Despite its comprehensive approach, China's system has experienced both successes and failures. It failed to predict the devastating 28 Sichuan earthquake, raising questions about the effectiveness of their methods. Yet Chinese authorities maintain that their integrated approach has successfully forecast several significant events and continue to invest in prediction research. In California, where the specter of the big one looms large in public consciousness, scientists have generally avoided specific predictions. Instead, the emphasis has been on probabilistic forecasting through projects like the Uniform California Earthquake Rupture Forecast. This approach estimates the likelihood of significant earthquakes along different segments of fault systems over specific time periods, valuable for long-term planning but not for immediate warning. In 2019, California finally implemented Shake Alert, an early warning system similar to Japan's. The system detects earthquakes as they begin and can provide seconds to tens of seconds of warning before strong shaking arrives. While not true prediction, these precious moments can be enough to automatically slow trains, open firehouse doors, or allow individuals to drop, cover, and hold on. These diverse case studies reveal a crucial pattern. The most successful approaches to earthquake forecasting combine scientific monitoring with public education and clear communication of uncertainty. Where these elements are missing, even accurate predictions may fail to save lives, or worse, create new dangers through panic or misunderstanding. At the heart of earthquake prediction lies a profound ethical dilemma: the life-saving potential of accurate forecasts versus the devastating consequences of false alarms or missed events. This tension creates what ethicists call a dual-use dilemma, knowledge that can both help and harm society depending on how it's applied. Consider the scenario faced by seismologists who detect possible precursors to a major earthquake in a densely populated area. If they issue a warning and evacuation orders follow, The economic and social disruption is immediate and guaranteed. Businesses close, productivity halts, and resources are diverted to emergency response. For economically vulnerable populations, even a few days of lost income can be catastrophic. Hospital patients may face risks from hasty relocations. Traffic accidents during evacuations may cause injuries or deaths. If the earthquake doesn't materialize, public trust erodes. The cry wolf effect might lead people to ignore future warnings, even legitimate ones. In 1976, after noting concerning precursors, Chinese officials evacuated Tangshan. When no earthquake occurred immediately, many residents returned home just before the catastrophic quake struck. The prediction was essentially correct but imprecise in timing, with tragic consequences. Conversely, if scientists observe potential warning signs but remain silent to avoid causing unnecessary alarm, they risk being blamed for preventable deaths when an earthquake does occur. This act versus omission distinction carries enormous psychological and legal weight, as demonstrated by the L'Aquila trial. Society often judges failures to warn more harshly than false alarms, even when statistically they represent the same level of predictive error. This asymmetry is compounded by the challenges of communicating scientific uncertainty. Seismological predictions rarely fit the binary will happen, won't happen format that public officials and media outlets prefer. Instead, they typically express probabilities. A 5% increase in the likelihood of a major event over the next week, for example. Such nuanced statements can be easily misinterpreted or sensationalized. The ethics of earthquake prediction also intersect with issues of equity and environmental justice. Wealthier communities can better withstand both false alarms and actual earthquakes. They have insurance, savings to weather economic disruption, and buildings constructed to stricter seismic codes. When prediction systems are deployed, questions arise about who receives warnings first and whether marginalized communities have equal access to protective information and resources. Cultural contexts further complicate the ethical landscape. In some societies, fatalistic attitudes toward natural disasters may reduce compliance with evacuation orders. In others, historical experiences with government mandates may affect public trust in official warnings. Religious or traditional beliefs about disaster causation may influence how warning messages are received. Effective prediction systems must account for these social factors, not just geophysical data. Ethical considerations extend to research priorities as well. Given limited resources, should we invest in prediction technology that might occasionally save lives through advanced warning, or would those resources save more lives if directed toward improving building standards, retrofitting vulnerable structures, and enhancing emergency response capabilities? The most sophisticated earthquake prediction system cannot prevent casualties if buildings aren't constructed to withstand shaking. For individual scientists, these dilemmas create personal, moral hazards. Publishing research on potential precursors might advance scientific understanding, but could also trigger public fears if misunderstood. Remaining silent about preliminary findings might avoid unnecessary panic, but could mean missing opportunities to test and improve prediction methods under real conditions. Professional scientific organizations have responded by developing ethical guidelines for earthquake prediction research and communication. These typically emphasize transparency about uncertainties, peer review before public announcements, coordination with emergency management agencies, and sensitivity to socioeconomic impacts. Yet these guidelines provide limited protection when scientists face pressure from political authorities, media inquiries, or their own conscience during unfolding seismic crises. When a team of Russian and American scientists identified seismic patterns suggesting a significant earthquake might strike the Kamchatka Peninsula within 5 years, they faced an immediate communication dilemma. Publishing in scientific journals would fulfill their academic obligations, but might not reach those most at risk. Speaking directly to the public risked misinterpretation. Working through government channels meant surrendering control over how their findings would be presented. Each pathway carried distinct ethical implications and potential consequences. This scenario illustrates the central challenges in communicating earthquake forecasts: technical complexity, uncertainty, competing stakeholders, and life or death. Implications. Unlike many scientific communications that can afford academic detachment, earthquake predictions directly affect human behavior and policy decisions, often under intense time pressure. The language of seismology itself creates the first barrier to effective communication. Terms like recurrence interval, moment magnitude, liquefaction potential, and seismic moment are precisely defined for scientists but often misunderstood by the public. Even seemingly straightforward concepts like aftershock have specific technical meanings that differ from colloquial usage. When scientists say an aftershock sequence might last months, residents might hear this as a prediction of continued danger rather than a normal pattern of decreasing risk. Probability statements. Present particular difficulties. When seismologists express forecasts as statistical likelihoods, a 30% chance of a magnitude 6 or larger earthquake in this region within 1 week, they convey scientific precision. But probability remains notoriously unintuitive. For human psychology, is 30% a concerning risk or a reassuring unlikelihood? Different audiences will interpret the same probability statement in radically different ways based on their prior experiences, risk tolerance, and immediate circumstances. Media coverage frequently exacerbates these communication challenges. The news cycle rewards definitive statements and dramatic narratives rather than nuanced probabilities. Headlines simplify complex findings, sometimes distorting their meaning entirely. In 1990, when USGS scientist Alan Lind noted an increased probability of an earthquake along the San Andreas Fault near Parkfield, California, some news outlets reported it as a definitive prediction. When the earthquake didn't occur within the time frame many had inferred, public trust suffered, despite Lind having expressed his findings as probabilities, not certainties. Social media has further complicated the landscape. Information and misinformation now spreads at unprecedented speed. After a significant earthquake, unverified predictions of aftershocks or follow-on events often circulate widely online, sometimes attributed to legitimate scientific organizations that made no such statements. Scientists must now contend not only with communicating their own findings accurately, but also with correcting viral misinformation. In real time, cultural and linguistic differences add additional layers of complexity. Translating technical seismic terminology between languages can introduce subtle but critical shifts in meaning. Words that express uncertainty or conditionality may have different connotations across cultures. Even the cultural understanding of authority and expertise varies, affecting how seriously warnings are taken and which sources are trusted. The timing of communications presents another strategic challenge. Early warnings based on preliminary data might save more lives but carry greater uncertainty. Waiting for more complete analysis reduces false alarms but may come too late for effective action. This temporal tension has no perfect resolution. It requires context-specific judgment, considering both scientific integrity and public safety. Effective earthquake forecast communication requires collaboration across disciplines. Seismologists provide the technical foundation, but social scientists, emergency management professionals, community leaders, and communication specialists all play crucial roles in translating scientific information into actionable guidance. This interdisciplinary approach recognizes that earthquake prediction is not merely a geophysical challenge, but a socio-technical system embedded in specific cultural contexts. The most successful communication strategies employ multiple channels, consistent messaging, clear visualization of uncertainties, and two-way dialogue that addresses community concerns. They avoid both excessive reassurance and alarmism, instead fostering realistic preparedness. Most importantly, they build trusted relationships between scientific institutions and communities before crises occur, creating foundations for effective communication when minutes matter. The next frontier in earthquake prediction combines approaches once considered separate domains: artificial intelligence, crowdsourced data collection, geological fieldwork, and space-based observation. This convergence promises more accurate forecasting by addressing the fundamental challenge of earthquake prediction, the need to integrate vast, heterogeneous datasets to identify subtle patterns across multiple scales. Machine learning algorithms are increasingly capable of detecting signals human analysts might miss. By training on historical earthquake data, these systems can identify correlations between seemingly unrelated precursors. One promising application uses neural networks to analyze the acoustic emissions from laboratory rock samples under stress, learning to predict failure points before catastrophic slippage occurs. Scientists at Stanford University and the Massachusetts Institute of Technology are working to scale these laboratory insights to real-world fault systems, though significant challenges remain in bridging these different scales. Distributed sensor networks represent another revolutionary approach. Traditional seismic monitoring relies on expensive, precisely calibrated stations, but researchers at the University of California, Berkeley, have demonstrated that even consumer-grade accelerometers in smartphones can detect earthquake motion when networked together. Their MyShake application turns ordinary smartphones into seismic sensors, potentially creating dense monitoring networks in populated areas where traditional coverage might be sparse. Similar citizen science approaches are being developed for other potential precursors, from groundwater changes to electromagnetic anomalies. Space-based technologies offer perhaps the most transformative potential. The European Space Agency's Sentinel-1 satellites use radar interferometry to measure ground deformation with millimeter precision across entire fault systems. NASA's GRACE-FO, Gravity Recovery and Climate Experiment Follow-On mission, can detect minute changes in gravitational fields that might indicate mass redistribution before earthquakes. Thermal infrared sensors on meteorological satellites have occasionally detected temperature anomalies preceding major seismic events, though the mechanism remains poorly understood. Genetic algorithms are being employed to integrate these diverse data streams, adaptively weighting different precursors based on their predictive success in different geological contexts. Unlike traditional forecasting models built on predetermined rules, these systems evolve their own prediction strategies through iterative testing against historical data. Early results suggest they may outperform conventional statistical approaches, particularly for complex fault systems with multiple interaction patterns. Quantum computing presents a more speculative but potentially revolutionary tool. Earthquake prediction requires modeling chaotic, nonlinear systems with numerous variables, precisely the kind of problem where quantum algorithms offer theoretical advantages. While practical quantum systems with sufficient capacity remain years away, preliminary work suggests they could eventually simulate fault dynamics at unprecedented levels of detail. These technological advances are complemented by innovations in risk communication and decision support systems. Interactive visualization tools now allow emergency managers to explore different earthquake scenarios and response strategies. Automated alert systems can tailor warnings to specific locations and vulnerabilities. Mobile applications can provide personalized safety instructions based on a user's immediate environment. Despite these promising developments, fundamental limitations remain. Earthquake processes occur deep within the Earth, where direct observation is impossible. Significant events are relatively rare, limiting the training data available for machine learning approaches, and the complex, chaotic nature of fault systems may impose theoretical limits on predictability, regardless of technological advances. Recognizing these constraints, many researchers have shifted focus from deterministic prediction, specifying exactly when and where earthquakes will occur, toward operational forecasting systems that continuously update probability estimates as new data arrives. This approach, analogous to modern weather forecasting, acknowledges inherent uncertainties while still providing actionable information. Japan's continued investment in its early warning system exemplifies this pragmatic approach. Rather than promising perfect prediction, Japanese authorities have created a system that delivers timely alerts, educates the public about appropriate responses, and continuously improves through technological innovation and social learning. Their experience suggests that the most effective earthquake forecasting systems will be those that balance scientific ambition with practical utility, integrating technical capabilities with social needs. As climate change alters stress patterns, through changing sea levels, groundwater conditions, and glacial melt, earthquake forecasting faces new challenges. Models trained on historical patterns may become less reliable in unprecedented geological conditions. Addressing these emerging complexities will require even greater integration across scientific disciplines, from seismology to climatology to social vulnerability research. In the mountain village of San Giuliano di Puglia, Italy, October 31st, 22 was meant to be an ordinary school day. Without warning, a 5.9 magnitude earthquake collapsed the recently renovated Francesco Giovine school, killing 27 children and a teacher. The tragedy sparked national reform of building codes and emergency response protocols. It also crystallized a profound truth often overlooked in technical discussions of earthquake prediction. The ultimate measure of success is not scientific accuracy, but human lives saved or lost. This human dimension of earthquake forecasting extends far beyond the moment of seismic crisis. It encompasses years of preparation, seconds of warning, days of emergency response, and decades of recovery. At each stage, the effectiveness of prediction and warning systems depends not just on geophysical accuracy, but on human factors: training, trust, communication networks, and community resilience. Consider the contrasting outcomes of similarly powerful earthquakes. The 7.0 Haiti earthquake of 2010 killed over 200,000 people, while the 6.9 Kobe earthquake of 1995, in far more densely populated Japan, resulted in approximately 6,000 deaths. The difference reflects not predictive capacity, but preparedness, building standards, emergency services, and social infrastructure. The most sophisticated earthquake prediction system cannot compensate for vulnerable physical infrastructure or inadequate emergency response capabilities. This reality has led many experts to advocate for a more holistic approach to seismic safety. Rather than viewing prediction as a standalone solution, they integrate it within comprehensive disaster risk reduction frameworks. These approaches combine multiple strategies: identifying hazards, reducing vulnerabilities, enhancing response capabilities, and building long-term resilience. Prediction becomes one tool among many, valuable primarily when it enables practical, protective actions. The psychological dimensions of earthquake forecasting are equally important. Human responses to warnings are shaped not only by the warning itself, but by cognitive biases, social influences, and prior experiences. The normalcy bias leads people to underestimate risks and assume situations will resolve normally despite warnings. The optimism bias causes individuals to believe they face less risk than average. These psychological tendencies can blunt the effectiveness of even technically accurate predictions. Trust emerges as the critical factor mediating between scientific capability and social benefit. Communities that trust scientific institutions and government agencies are more likely to heed warnings and take protective action. This trust is built through transparency, consistent communication, and demonstrated competence before crises occur. It can be rapidly destroyed by perceived failures, exaggerated claims, or politicized messaging. The most sophisticated prediction system will fail if the resulting warnings aren't trusted by those at risk. Indigenous and traditional knowledge systems offer valuable perspectives often overlooked in technical approaches to earthquake forecasting. Many communities living in seismically active regions have developed cultural practices and observational techniques refined over generations. In parts of the Andes, traditional knowledge includes attention to unusual animal behavior, groundwater changes, and atmospheric conditions that modern science is only beginning to investigate systematically. Integrating these knowledge systems with contemporary scientific approaches could enhance both prediction capabilities and community engagement. The economic implications of earthquake forecasting create additional complexities. Property values, Insurance rates and investment decisions all respond to perceived seismic risk. A prediction system that reduces casualties but triggers economic disruption may still impose significant hardship, particularly on vulnerable populations. These economic considerations must be factored into the design and implementation of warning systems. As we look toward the future of earthquake prediction, perhaps the most important shift is conceptual, moving from the idea of prediction as a binary technical challenge to understanding it as a socio-technical system embedded in specific cultural, economic, and political contexts. Success requires not just better sensors or algorithms, but better integration with human decision-making processes and social structures. The field increasingly embraces this integrated vision. The Global Earthquake Model Foundation, for example, combines scientific research with practical tools for risk assessment and community engagement. The Earthquake Early Warning for the U.S. West Coast project involves not just seismologists, but social scientists, emergency managers, and community representatives in system design and implementation. Ultimately, earthquake prediction exemplifies both the promise and limitations of scientific knowledge when applied to complex social challenges. It reveals that the most difficult questions are not simply technical, but ethical, balancing different types of risk, respecting diverse values, and distributing benefits and burdens equitably. How we navigate these questions reflects not just our scientific capabilities, but our values as a society. The science of seismic forecasting continues to advance, but its most profound lessons transcend geophysics. They remind us that in facing Earth's most powerful forces, our greatest resources may be human ones. Cooperation, communication, compassion, and the resilience of communities united in preparation for whatever tremors the future may bring.